Hi, welcome back to the next video in the IB Physics Standard Level and Higher Level series. Today, we'll be looking at simple harmonic motion, which is topic C.1. So let's begin. This is one of the easier topics, but it's also a really important topic, so getting to know this well is quite important to getting a good final grade. So I'm going to try and simplify this topic as much as possible because it's already quite easy, and I suggest you try and follow along because this is probably the most easy important topic in the IB Physics syllabus. So everything is an oscillation if it goes around and around, so if it's periodic. So an oscillation basically just means the variation of displacement with time about an equilibrium position. So if you look at this pendulum right over here, it's swinging from between B and C. And so if the equilibrium position, which means the middle of the oscillation, so that's A, if this is just going around and around like this, back and forth, then it's swinging about A. So that's basically what an oscillation is, the swinging about A. And there's a lot of nuances to this. We could analyze this in a lot of different ways, but I'll get a little bit more into that. But for now, you just need to know an oscillation is when you change displacement about the equilibrium. So this topic has quite a few new symbols and words, but they're all related to everything that we did in mechanics. So the symbols and words are displacement, which has a symbol x, and as you probably remember, that's the total distance from a point. In this case, that point is the equilibrium position, and it's measured in meters. Now, amplitude is just the maximum displacement. So this right here, if you see on this graph, the maximum positive displacement is the amplitude. So that's this point over here, this point over here, and this point over here. So it's labeled as A. The lowest displacement is just negative A. So when, for instance, in this, when we're at C, it's the farthest from A, so we'll call that A. And then when we're at B, we're the farthest from A in the negative direction, so that's negative A. The only convention I'm using here is that the right side is positive, and that's what you generally do. And then period is basically the time taken for a full oscillation. So the distance between the crests is how I remember that. So the distance from here till here is a period, but the distance from here till here is also a period. So it just means the time taken for the sine or the cosine curve to hit the axis 3 times if it's a sine curve, or 2 times if it's a cosine curve. So basically coming back to the same spot, right? So if we start here, the period ends here because it's a sine curve. If we start up here, the period ends here because it's a cosine curve. So either you need 3 peaks or 3 roots. And this is calculated by 1 divided by frequency. I'll get to what frequency is in just a second, so you don't really need to know how to calculate period right now. You should just know that it's the one full cycle, so 1 up and 1 down. And then the frequency is basically the number of oscillations you can do in 1 second. So again, if I timed this and let it spin freely for 1 second and I counted how many oscillations were done, so if it spun 3 times from A to C to B to A, that's 1 oscillation. And so if it did that 3 times, then the frequency is 3, if it did that in 1 second, that is. And this is the same as 1 divided by period. So frequency is actually measured in per seconds, which might sound weird, but we call that hertz usually. And equilibrium is basically just the fixed point, which is taken as 0 displacement. So everything is about the equilibrium. On this graph, it's this straight line right here, the x-axis, which is considered 0 displacement. Now you can ignore this for now because this is higher level content. I've just put that on there as like a peek into the future if you are higher level, but if you're standard level, please ignore it. So let's go on to calculating period. So to calculate period, you have 2 formulas. T equals 2 pi square root m by k, and this is for a mass spring system like this, where there's a spring, and the spring has spring constant k, and the mass of this ball here is the m, so the period would just be 2 pi times square root of m by the spring constant. So if the spring constant were 1, and the mass were 2, then we would have 2 pi times square root 2, which is just 2 root 2 times pi seconds for the period, or that's the exact value, right? And this formula right here is the exact same, but it's instead for a pendulum system. So L is the length of this string right here. So this is L. And then G is just gravity, so 9.81 in 99% of scenarios. If it gives you, say, a different planet, which they could do, you just have to calculate the G. So they'll give you the period. They'll say like it takes 1 second, find G, and then you just have to rearrange for G. So yeah, try finding the period for a pendulum of length 10 centimeters. I'll give you a moment to do that, and then I'll show you the answers. Okay, so the answer is we use this formula right over here because it's a pendulum and not a mass spring system, so there's no spring constant. So the pendulum has length 10 centimeters, and if you remember, length is always measured in meters, so we have to convert that to 0.1 meters, and we know that gravity is 9.81 meters per second square, so we plug those two numbers in, so it's 2 pi times square root of 0.1 divided by 9.81, which is the same as 2 pi times square root of 0.01019, which is as the same as 2 pi times 0.10096. This is the square root of this number right here. And if you evaluate this, you get around 0.634 seconds. And now let's just move on to something that's again quite familiar from mechanics. So angular frequency and angular displacement. Now angular displacement just means 2 pi. If you remember from a circular motion, if you go around in a circle, that's 2 pi radians. So angular displacement is just 2 pi radians. So for instance, from here till here, we completed a full period, which means that we were displaced by 2 pi radians, so we came back to the same point. And angular frequency is just 2 pi times f, so it's angular displacement times the frequency. And so basically this is again something quite similar from mechanics. The way this is derived is we multiply this w here, that's angular frequency, up here, which we get angular frequency by frequency is 2 pi, and then we multiply frequency to the other side, so we get angular frequency is equal to 2 pi f. And so these two formulas from the mechanics data section also apply to simple harmonic motion. So a velocity, linear velocity, is indeed 2 pi r by t, and this is actually the exact same as angular velocity times r. So if we ignored this 1 over f here and we rearranged t equals 2 pi by w for w, we would actually get 2 pi by t, which is w right here. And this again does apply, so linear acceleration is indeed linear velocity squared by r, is indeed angular velocity squared times r, and that is indeed 4 pi square r by t square. So you can use these formulas in this chapter as well. And there's basically two conditions of simple harmonic motion. So the conditions of simple harmonic motion is that there's a restoring force towards equilibrium, and that acceleration is directly proportional to the negative of displacement. So I'll touch on this first one initially. So for this pendulum to oscillate back and forth, there has to be something pulling it towards the center at the end. Otherwise, it would just go up infinitely and never come back down. So at this point, there's a force that's acting towards A here, and as it goes more and more out, that force grows. So it pulls towards A stronger until eventually it wins, and then the pendulum comes back to A. So that's the restoring force. And the second is that acceleration is directly proportional to the negative of displacement. That means the acceleration displacement graph is a straight line, which is the exact same as y equals negative x. It's just a straight line through the origin that has a negative gradient of 1. And yeah, that's pretty much that. And if you want to calculate that gradient, you have to rearrange this for a by x, and a by x is actually negative w squared. So this gradient right over here is negative w squared. So let's try solving an exam question on this. So a particle undergoes simple harmonic motion of period t. At time t equals 0, it's at equilibrium position. When is the particle at its greatest distance from the equilibrium position? So I'll give you a moment to try that out. Okay, so let's draw out this pendulum. So at t equals 0, we'll call this the equilibrium position, and the ball's here. And then we'll call this at this point over here and this point over here the two extremes of the motion, so a and negative a. It doesn't really matter which is which for this question because it's not asking about that. So at t equals 0, the particle is over here. And then at t equals to t by 4, because there's 4 motions here, right? One is from here till here. The second is from here till back here. The third is from here till here. And the fourth is from here till back here, which is the exact same as one cycle. So at t by 4, because this is 1/4 of the time, we're over here. And then at t by 2, we're back in the middle. And then at 3t by 4, we're over here. Right? And then at t, we're back in the middle. So we're in the middle at 3 of these times. So t by 8 is not even on this list, so we can cancel that off immediately. T by 2, we're in the middle, so we can cancel that off. And at t, we're in the middle, so we can cancel that off. That leaves us at 3t by 4. So that is the right answer. But we can see in our diagram, at t times 3 by 4, we're on the far left. And that is the greatest possible distance from the equilibrium position, because distance is a scalar. It doesn't matter if we're at the greatest possible leftmost distance or the rightmost distance. That really doesn't matter. The answer is hence C. I hope you found this video helpful. If you are standard level, that's all you need to know for simple harmonic motion. And please do let me know down in the comments below if you have any questions. As for the higher levels, I will release another video on the higher level only section coming soon. So yeah, stay tuned for that. Thanks for watching and have a nice day.